Hello, ladies and gents. This is going to be a series of videos that kind of review everything that we've been learning since the beginning of the year. Um, and I hope that this would be an easier way for you to review the stuff that we've been learning. Um, so I hope this helps. So the first lesson that I'm going to go over quite quickly, hopefully, is the lessons about types of numbers. This is the first thing that we talked about in algebra, and to be honest, you need to understand how numbers work, what numbers are, so on and so forth, so that when we talk about different types of numbers in the future, you understand where they come from. Okay? So, the big idea is we know all these types of numbers, and let me actually get my highlighter out. And we call these the real numbers. Okay? Any number that you can think of is a real number. And just for for quick clarification, we've learned about natural numbers, the whole numbers, the integers, rationals, and irrational numbers. And we're going to come back to this diagram at the end of this video, but this is where we're heading. What are the different types of numbers? And the first thing that, not too sure if we actually talked about this, but this is super important just to know like notation. There is a term called a set, and a set is defined as a collection of stuff. So, for example, in mathematics, when we want to write a set, we use these curly brackets. And let's say I'm going to have a collection of colors. So we have blue, we can have green, we can have yellow, okay? And you can close it with a curly bracket. We say that this whole thing is called a set. Now, in this example, this is a set of colors. Okay? But in mathematics, we would probably have a set of numbers. So we can have 1, 2, 3, how about 100? I guess that's it. We can just say that this is also just a set of numbers. Okay? The idea is a set is just a collection of stuff, and that collection of stuff we put inside of brackets, like a little home. Okay? So now knowing what a set is, let's jump into it. So natural numbers are, I think this is the best way to explain it, are just numbers that start with 1 and increases by 1. Okay? We talked about this in class, like the first set of numbers that people came up with are numbers that you can kind of count on your hands, like 1, 2, 3, 4, 5. But in other words, if you keep adding 1 to any number, you get another number, right? So if I have the number 10, if you add 1 to that, you get 11. Add 1 to that, you get 12. And you can do that infinitely. So if we want to use set notation, which again, we're going back to this idea of what a set is, we can say that the natural numbers is a set of numbers that start with 1, 2, 3, 4. And you see how I'm defining that each number is just one more than the next? 5, 6. Now, I can't sit here forever and write an infinite amount of numbers. That's impossible. So we're going to put dot, dot, dot to show that it goes on forever. And that's it. Natural numbers are just numbers that start with 1 and increase by 1 infinitely. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, infinitely. Okay? Then we are building on that. So now we have whole numbers. Whole numbers are the natural numbers, but now we have 0. So if I mention a whole number is the set of numbers, but now we can start with 0. So whole numbers are 0, 1, 2, 3, 4, 5, so on and so forth. Okay? The difference between natural numbers and whole numbers is that natural numbers does not include 0. Whole numbers do include 0. Okay? Now, if you notice, we're building on these ideas. Natural numbers start with like 1, go on infinitely. Whole numbers is the other set of numbers that now starts with 0. Okay? Now we're up to integers. Integers we're going to see throughout the entire year. Okay? Integers are positive and negative whole numbers. So if we think of a number line, let's see if I can do this. Oops. Let's see if I can do this really neatly. Oh, that didn't really help. Okay. Okay, that sucks. We'll just do this. So if I have a straight line, okay, and my whole numbers, normally we start here at 0. Then we go 1, 2, 3, so on and so forth. Integers are saying, well, let me put an arrow. Integers are saying, well, we can go the other way now. So before 0 is -1, -2, -3, and so on and so forth infinitely. If we had to write a set, or using set notation, we can say we're starting from like negative infinity. We have -3, we have -2, we have -1, we have 0, we have 1, we have 2, and so on and so forth. Do you see in this notation we have an infinite amount of numbers over here and an infinite amount of numbers over here, and we're just representing all the numbers that we call integers. So again, integers are positive and negative whole numbers. Okay? Now we're going to get into the juicy stuff. Rational numbers. So I kind of pre-wrote everything. So rational numbers, and I'm going to highlight this because these are the big ideas, okay? Rational numbers are numbers that can be written as a fraction, okay, where the numerator and denominator are integers. We know integers mean positive and negative whole numbers. So we could say this differently by saying numbers that are rational can be written as a fraction where the numerator and denominators are either positive or negative whole numbers. So let's do an example or two of that. Let's pick this purple color. Okay. So, example. 3 divided by 4. Is it a fraction? Yes. Are the numerator, remember the numerator is the top number, and denominator is the bottom number? Are the numerator and denominators integers? Meaning, are they either positive or negative whole numbers? Yes. 3 is a positive whole number, and 4 is a positive whole number. So this is rational. How about, let's say, -11 divided by 4. Is this a rational number? Well, it's a fraction. The numerator is a negative whole number, and the denominator is a positive whole number. So they're integers. So this must be a rational number. Okay? So that's one way we can define a rational number. Another way we can define a rational number is if it's written as a decimal. So if the decimal terminates, and terminates, if you don't remember, means ends. So if I write, so as for an example, if I write 3.221, is this rational? Okay, so it's not a fraction, but it is a decimal. And does the decimal end? Yeah, it doesn't go on forever. How about another example? How about if we do 2.9937114. Okay, so it's not a fraction, so it's a decimal. Does it terminate? Yeah, it ends. I didn't put a ... at the end. So it's because it ends, it must be rational. This is the last one. So if it's a decimal, it either is going to terminate or it's going to have a pattern. So if I have, for an example, if I used, let's say, let me choose a different color. I'm tired of this color. Okay. If I did 3.12121, what do you notice is happening? 1, 2 is repeating. So you might see it like this with a bar on the top indicating that these two numbers repeat over and over again. Or you just might see a dot, dot, dot to show that it continues. If we do another example, I'm going to choose a different color just so we can be a little bit more exact. Let's not do that. Let's do this. Okay. If we did negative 13.19731973 dot dot dot. Do you notice if there's a pattern? Absolutely. This 1973 keeps repeating. So, is it rational? Well, it's a decimal, and the decimal has a pattern. So it must be rational. Okay? Irrational numbers are not rational. So there's two kind of definitions, or I wouldn't say definitions. They're kind of like requirements. Like how could you tell if it's irrational or not? So the first way is, well, if it's a square root of a number, that's not a perfect square. So, for example, if I said the square root of 4, is that a perfect square? Meaning, is there one number that you can multiply by itself to get you 4? The answer is yes, 2. So the square root of 4 is 2. But that's a perfect square, so that can't be irrational. So this is not an example. However, if I gave you the example of, let's say, the square root of 3. Is 3 a perfect square? Meaning, can you find two numbers that are the same, that when you multiply them together, get you 3? The answer is no. In fact, if you actually put this on your calculator, you're going to get something that's going to actually be over here in just a second. So, because this number is not a perfect square, this number must be irrational. So another example could be the square root of 12. Is 12 a perfect square? In other words, is there one number that you can multiply to itself to get you 12? 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. I already passed 12. So there is not one number that you can multiply to itself to get you 12. So this number must be irrational. Okay? So another way that we can tell if a number is irrational is if the decimal actually, let me highlight this. So if the decimal does not terminate, meaning it goes on forever, and does not have a pattern. So previously, rational numbers, it can be a decimal that either stops or it has a pattern. Irrational numbers could be a decimal that goes on forever but does not have a pattern. So, for example, if I said 3.112314599176 blah 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 and going on forever, is there any pattern here? Is there any part of here that repeats? Yeah, there are a lot of ones, but there's no pattern here. Just like if we looked at before, clearly 1 2 1 2 1 2, that's a pattern. 1973 1973 1973, that's a pattern. But over here, if you're looking at these numbers, there are absolutely no patterns here. One more example. If I do negative 71.31811893742 dot 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 dot. Yeah, there's a couple of 8s, there's 9s, but there's no defining pattern. For example, if I said, hey, what number is going to be after 6? You don't know. However, if we looked at this one and I said, okay, 3.121212, what's going to be the next number? You can clearly say it's going to be 1. Okay? So an irrational number is a number that could either be a decimal number that does not end and that does not have a pattern. And an irrational number is, well, it could be a square root of a number that's not a perfect square. And you know what? I want to give another example. Okay? So what type of number, by the way, I know this is used as a hashtag, but this also means number. So what type of number um, is the following? Okay, I'm going to give you two examples. So number 1 is over here, number 2 is over here. Then we're going to wrap it up. Okay, let's use pink. So if I said, let's say I gave you 3 over negative 11. Okay, so is it a natural number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. No, this is a fraction. So if it's a fraction, it's not a whole number, and it's not an integer, right? Fractions only live in rational numbers, and irrational numbers, technically, but we'll get there in a second. So is the numerator and denominator integers? Yes, 3 is a positive whole number, and 11 is a negative whole number. So this must be rational. What if I gave you the number, let's do 3.112112112, so on and so forth. Well, it's a decimal number, so it has to be either rational or irrational. And for rational numbers, if we're looking at decimals, we want to see if it terminates or has a pattern. Well, it doesn't terminate because obviously this is saying that it's going on forever. But does it have a pattern? Well, a good way to know is ask yourself, do I know what the next number is going to be? 112, 112, 112. I have a feeling it's going to be 112, right? It repeats this pattern over and over again. So this number must also be rational. Let's do a third example. So, what if I did 1.1379246118132, so on and so forth? Well, it must be either rational or irrational because it's a decimal. It goes on forever. Is there a pattern? Or in other words, do I know what the next number could be? I have no idea. There is no pattern here. So this must be irrational. I hope that this helps break down what each type of number is and how you can tell just by looking at one number how we could describe it. Again, every number that we've learned is called a real number. This most simplistic number or set of numbers are the natural numbers. And throughout many, many years, we added on different rules and different types of numbers to create new types of numbers. So if we add or if we put a 0 into the natural numbers, we get the whole numbers. Once we start talking about fractions, I'm sorry, not fractions, integers, those are positive and negative whole numbers. And last but not least, rational numbers. And integers, sorry, not integers, but irrational numbers are numbers that are not rational. So I hope that this helps. Please feel free to go back into the video just to look up the different definitions and the different examples that we used. I hope you have a great rest of your day, and I'll see you later.